Okay, so we're heading up to 1 p.m. Eastern Standard Time for those who are joining us. Thank you so much. I'm really excited for this one. I see some familiar faces. Lou, welcome back. Bouye as well. I saw you this morning, so it's good to see you guys back. And glad to see you're not too Zoom fatigued for the second workshop today. Couple housekeeping notes. As I mentioned, for those who are joining, I know we're going to have some people streaming in. But I won't keep you waiting. We'll get started shortly. Make sure to check the link for Hopin for the event tomorrow as well. There's a couple different companies and groups who will be presenting, or rather we'll have a virtual exhibit. So they usually give away some prizes. And funny enough, although it only takes a click to go into their little virtual booth, and there's usually a couple gift cards from Amazon and so on, some around the range of $100 Canadian. Not that many people actually go and do it. So if I could recommend one thing, it would be to go in and click. You'd be surprised. There's actually not a whole lot of people. It's for this particular session tomorrow. It's a little bit of a smaller, more intimate group. It's in part because we're doing this in July where everybody's on vacation, but also because we launched a little late on the schedule and the invitations. But that's not a problem. It's actually going to be nice. It's going to be nice to see some of the sessions and some of the more intimate questions and Q&A that we can allow for, given the smaller group sizes. Last thing I'd mention, and I know I mentioned this morning, so please feel free to drown me out and ignore me if you find myself repeating. But I say this a lot. It's really important to ask questions. Regardless of where you are in your journey, I think you'll find that the speakers are all very patient. So if there's something that is on your mind, you're not sure, you would want to clear something up or ask a question, and it would help you absorb some of the content from today. I would recommend that you put yourself out there and ask a question. Nobody's here to judge, and trust me, there's people here from different vantage points, different areas, different professional backgrounds, and there's no judgment, so it's okay to ask questions. I think that'll be dependent on the value that you get is directly proportional to the questions that you're asking. And that's subjective based on where you're at in your personal or professional career. So I hope that we can, fall out of our comfort zone a little bit and make sure we're engaging. So that being said, I'm really excited about this one. I'm really excited to welcome Ali. I've known Ali for a while now. I know that his work is fantastic. And I was very grateful that he'd take the time to share with you his work this afternoon. In his presentation today, his workshop's on Introduction to Graph Neural Networks and its application in drug discovery. So before I let Ali take the stage, I wanted to give you a quick primer and background for those who aren't familiar. Ali Madani is the head of machine learning and his team at Cyclica. He heads the machine learning at his team at Cyclica Inc. He leads the team to further improve Cyclica's machine learning technology for drug discovery. And as a computational biologist and machine learning specialist, Ali has worked on a series of scientific articles in high-impact scientific journals and international conferences covering such fields as transfer learning, dimensionality reduction, and unsupervised clustering. He earned a Ph.D. degree from the University of Toronto and a Master of Mathematics degree from the University of Waterloo. I think you're going to really enjoy this session. I'm happy and grateful to present. And Ali, thank you so much for taking the time today.
No problem. Thanks, Dave, for the introduction. And honestly, thank you again for organizing such amazing events. So from you, for us, all the team, I appreciate your effort for sure. So could you hear me well?
You're most welcome. I can hear you, and I'll be around just to help field questions as they come in, but perhaps as you're going, we could take a couple pauses, particularly in high dense portions of the workshop, so we can gauge some questions from the audience. And thank you, Ali. It's actually the Vector Institute who helped chair and organize this one as well. So thanks to the folks at the Vector Institute. But yeah, no, great. I'll pass the torch over to you, and yeah, I hope you have fun and enjoy.
One thing, Dave, I cannot share my screen. I think there's a.
Okay, let me see. Oh yeah, might be my fault to just pass over the duties to you. So I'm just going to get the host key. It'll just take a minute while I retrieve that. And while I'm doing that, maybe Ali, did you want to give us a primer on who you are, maybe a bit of a bio?
For sure. So a little bit of background from myself. I did my master's, as Dave mentioned, in University of Waterloo. I did a master's of mathematics working on stochastic processes in biological problems, specifically about cancer cell growth. And then I became very much interested in machine learning. More and more I knew about its theoretical aspects, and I wanted to work in the practical aspects. So I came to University of Toronto to work on my PhD, focusing on machine learning in precision oncology. So I worked with quite different kind of data types during my PhD: genomics, epigenomics, some proteomics data and metabolomic data, to try to tackle the problem of precision oncology. If you are from similar areas, you know it is a very much complicated problem. Definitely we couldn't solve it, but we did as much as we could. And then I joined Cyclica at the end of my PhD, and right now I'm the head of machine learning at Cyclica Incorporation. As Dave mentioned, we work on drug-target interaction problem from a machine learning perspective. So we developed a technology called Matchmaker. Matchmaker is deep learning technology. Definitely there are some feature processing and data engineering behind it, but at the end of the day, we provide those kind of data to a deep learning system and try to learn from information we get from drugs, small molecules, ligands, and target proteins, and try to predict interactions between them. So as you know, that any sort of machine learning pipeline development, machine learning modeling industry is beyond just performance improvement and trying to just see if we can get a good performance. There are many, many aspects around it, like explainability, feature analysis, all those kind of things. So we work on different aspects of machine learning pipeline development industrial level. So yeah, so actually, I think I wanted to get some information about you. It seems that we have around 60 participants, so it may not be possible to go through all of you, but let me give you a gist of what's going to happen in this workshop. So to make sure we're all on the same page, I'm going to cover different aspects, theoretical aspects, application of graph neural network, applying graph neural network using PyTorch, and some theoretical aspects even in graph level. So what graph means and why we care about graphs and why do we want to use graphs. Some part of it could be just a review for you if you already know about some aspects of it, like what graph means or those kind of stuff. But bear with me, we get into more exciting level as we go. Thank you. Okay, so before we start and while we are waiting for Dave, let me see. Oh, I can share my screen. Awesome. So then let's jump into it. So let me see. Okay, perfect. So as Dave said, it is an introduction to graph neural networks and its application for drug discovery. I'm going to cover some aspects of general graph neural network modeling, and then application in healthcare, and then an application in drug discovery in specific. So I talked about my background. I'm not going to get into more details, but if you are interested, please follow me on LinkedIn. I would be happy to be connected with you on LinkedIn. So this is the link, is AM Learning. So Ali Madani Learning. And then on Twitter, you can also follow me. It's Ali Madani with 2 underlines, because my name is definitely not unique. So maybe you've had that issue as well. So I had to use these 2 underlines. This is about me, but before we get into the workshop, I wanted to also talk a little bit about our company very briefly. So Cyclica is a Toronto-based venture-backed biotechnology company that has built and commercialized an integrated AI-augmented drug discovery platform that embraces the complexity of disease to accelerate the discovery of better medicines. But this is in business level, but all the time we try to provide our knowledge and expertise for people, like in this workshop, to make sure that actually we are democratizing the knowledge. So we want to make sure other people can follow us and can follow the same path to discover more, to be able to help. So, and we try to provide our knowledge and our expertise and our experience through papers, workshops, webinars, and talks. And thanks to TMLS community and Dave and all the friends and Vector Institute, this is one of those workshops that we try to provide some introduction about graph neural networks and how we can use it in healthcare and in drug discovery. So again, you can follow us on LinkedIn and Twitter, and it will not be a personal page. It is our company page, and you can learn about available job opportunities. We are a growing company. We have available job opportunities. If you check our website, our most recent advancements in AI-based drug discovery, we started blog post series, so you can check that as well, and our collaborations and successful stories in the area. So let's get into the interesting and exciting part of the workshop, which is, first of all, why we care about machine learning. But I don't want to get into very high-level introduction and history. I want to use it for the sake of this workshop. We need to answer a few questions before any sort of pipeline development. First of all, why do we want to use machine learning? For example, predicting drug target interaction, as we do in Cyclica. Maybe you want to predict survival of cancer patients. Maybe you want to predict, for example, which drug in precision medicine setting, which drug works for a heart disease patient or for Parkinson's disease patient. The next question, which is very important, is could we use machine learning for that problem or not? And most important part of answering that question is, do we have the data for it? One question, predicting drug target interaction. Yes, we can work on that. We can use machine learning for that. We have good amount of data to develop such kind of models to predict drug target interaction. Could we predict the effect of COVID-19 on each person in 20 years? Probably not, because it's been only 1.5 years. We are getting close actually to 2 years, unfortunately. But it's been 1.5 years that we've dealt with this disease. So we don't know what's going to happen in 20 years to the patients. Maybe nothing. Maybe they'll actually have risk of other diseases. Do we have the right data for the target problem? Again, predicting which COVID-19 patient will not survive more than 50 years is not possible. So right now, because we don't know what's going to happen, but predicting drug target interaction or many other problems is possible. And that's a very important thing, because nowadays we care a lot about machine learning in healthcare because we have data to use machine learning in healthcare setting. So starting from human genome projects, we started. So there has been a start in generation of omics data type. And then there has been collection of clinical data, and then putting all these kind of information or structural bioinformatics kind of information together helped us to develop machine learning models, statistical models, in general computational models for any sort of relationship identification and prediction in machine learning scenario. But there are two other questions, and one of them help us to realize why we care about graph neural network. One of them is, what is the best category of methods for the data type at hand? The last one for sure is, what is the best model for the target problem? So the last question is just a matter of modeling, doing parameter optimization, hyperparameter optimization, and identify our best model. But before that, the question is, what is the best category of methods for the data type at hand? One famous problem we all know is image classification. What is the best category of methodologies for image classification? Definitely convolutional neural network. Although graph neural network has been also used for this problem for image classification. But before that, people were using random forests and try to come up with some feature engineering and then putting those engineered features into random forests or other methodologies. And it didn't work well, but with convolutional neural network, which in this case, in this example of image classification, is maybe the best category of methodologies, we could solve the problem of image classification. And by solving, I mean we could achieve high performance. So that's the reason we care about this workshop, because graph neural network is the best category of method, is the best category among the methodologies for some specific problems that we want to rely on graphs. So in this workshop, maybe the titles will not be there exactly, but we're going to cover these different aspects of graphs, graph neural network modeling in general. First, why do we use graphs? Then we want to understand what could we use graphs for, because it's very important. Sometimes, maybe in academia more often, people jump into a very exciting new methodology just for the sake of examining it. But we know in industry that's not necessarily possible, because we have to first get a good understanding behind the problem, use an effective methodology to get high performance, and also we have to consider computational cost, interpretability, and explainability, and many other concepts of any sort of machine learning problem solving. So we are going to go through some introduction to neural network modeling, not very much, very briefly, to make sure we're all on the same page. We want to understand why classical neural network models cannot be directly used for graph modeling, although cannot be used is a very kind of big claim. It's not about cannot be used, it's mainly about why we prefer to not use those models, because they will not be effective. And then we're going to go through introduction to graph neural network, application of graph neural network in drug discovery and in general in healthcare. I'm going to talk about our recent paper in Cyclica Incorporation in collaboration with Vector Institute on graph neural network and drug discovery for COVID-19. So we came up with a drug that we provided in the manuscript, and we think it is an effective drug. Also, for any sort of drug development, there are many, many obstacles and barriers before getting a drug into a clinical setting, and maybe it fails in the process. And also graph neural network modeling in PyTorch for sure. So this is a very important part of this workshop, to make sure you know how to use PyTorch for GNN modeling in general. First of all, why do we use graphs? So we use graphs because we care about the relationship between entities. So if you go to traditional kind of machine learning setting, we have a specific set of features, and we just care about the relationship between those features, and then try to predict a specific classes or outputs for data points. But inherently, for some problems, we have some relationship between data points themselves that we know beforehand, like proteins. In proteins, we know amino acids are connected together with chemical bonds. So that exists, that chemical bond exists. It's not something that we statistically want to infer. It is something that exists physically. So could we benefit from it for any sort of protein-related machine learning modeling? So we have residues within proteins. So with chemical bonds, we can identify some of the relationship between them, and maybe we can benefit from them to do any sort of residual level prediction or protein level prediction. We have family trees based on genetic information of people, and many, many other examples in healthcare. Also in non-healthcare setting, we have, for example, social networks, or we have networks of roads and cities for trip planning. Definitely for many of these problems, we can use non-graph neural network models, but the question is, are they effective? So what is a graph? So we talk about graph, but let's review what a graph is. So graph includes many parts, but they can be summarized in 3 different categories. One, graphs have nodes, or vertices. So those nodes or vertices could be data points themselves, or it could be parts of data points. Imagine we care about proteins. So proteins include residues. So if we care about protein, we can have graphs in residual level. So nodes will be parts of a data point, because the data point is the protein. But if we care about the residues, we can consider nodes to be the data points or residues themselves. So it's just a matter of in what level we want to use those nodes. We have edges that connects the nodes together, right? It is clear we have co-expression networks, we have networks of residues in proteins, and those edges could be undirected or directed. So undirected means we don't have any sort of causality in relationship between the nodes. So for example, in co-expression network, we know that there's a connection. In protein network or residue, we know that there's a connection. There is no such kind of causality to say that, okay, if this node gets a higher value, then eventually that node gets a higher value. So we don't have such kind of thing, but sometimes we have causal relationships. So the third part is about those edges to be weighted or unweighted. So we have two general important information nodes and edges, and the third one is what kind of edges we want to use. So weighted or unweighted. Again, for proteins, we have chemical bonds. Those chemical bonds could have different weights. Or in physical space, we may have distance, and distance could be considered as a weight in the graph. So these are just some visualization to understand what's going on behind these terminologies. We have undirected graph. So nodes are connected to each other. There is no direction, and we have edges between the nodes that we know beforehand they're connected to. And we have directed graphs that has some sort of causal relationships between the nodes. We have source or parent node and destination or child node, depending on the kind of graph that we work with. So it means that there is a causal relationship, for example, between this red node and blue node, right? And then we have weighted edges sometimes. Sometimes it is not very common necessarily, but weighting the edges could be sometimes helpful because it means that there are some information we are losing. Maybe those information will be helpful in our modeling. Let's get into a little bit of math because later on it will help us to understand, for example, why we prefer to not use multi-layer perceptrons for graph neural network modeling. So first of all, we have node vector. Okay, what is node vector? So it just tells us about characteristics of the nodes. So here we have an undirected graph, node 1, node 2, node 3. It just tells us, okay, there's a value for node 1, there's a value for node 2, there's a value for node 3, although each one of these ABC could be a vector. And we will see later, we can have features for each one of the nodes. So each one of the node may have multiple values. So we can have assigned features to each one of the nodes. Like in proteins, residues, or atoms could have charge, electric charge. Or we may have different kind of atom. Or for example, in genetics, we have genes. Genes could be mutated or not mutated. They could be active or not active, and so on. And we have also adjacency matrix. So node vector tells us about each one of the nodes independently. It's just a matter of, we have nodes. So what are the characteristics of those nodes? But it doesn't tell us about which nodes are connected to which one. So adjacency matrix tell us about that connectivity. So here, for example, all the nodes are connected to each other. And as we can see, we have node 1 connected to node 2, which is this element, and node 1 to node 3, and so on. And the diagonal elements are 0 because we don't have any self loop. So if there is a self loop, for example, for node 2, this element of 2 and 2 will be 1. But what's the difference between undirected and directed graph in case of mathematical notations? So again, node vectors, node features doesn't care about that connectivity or even direction or weights. But it matters when we get into adjacency matrix. So here we can see that we don't have a symmetric matrix anymore. So here we had a symmetric matrix. So if we had an edge from node 1 to 2, there was an edge also from node 2 to 1, because there is no direction. But in this case, because we have a direction, that directionality comes into the picture in adjacency matrix. And as we can see, we have an edge from node 1 to 2, but not from node 2 to 1. Okay, because we have an edge from node 1 to 2, not 2 to 1. Again, this is just a summary review of what's going on in graphs. Some other terminologies. When we want to categorize graphs, because it matters for some of the problems, you have to deal with cyclic graphs, you have to deal with acyclic graphs. So it would be important to know what are the differences between them. So the main difference between cyclic and acyclic graphs is containing cycle. So the name is there. Cycle is in the name of is in the terminologies. So cyclic has cycle, acyclic doesn't have cycle, and cycle is about going from one node and getting back to it. So if there is such kind of cycle, it is not considered as acyclic anymore. So let's see why we care about this terminology, because we have different kind of graphs that in any sort of graph neural network modeling may come to the picture. Maybe in some of the literature, you've seen bipartite graph. So in bipartite graph, the main thing that matters is lack of connection between these nodes, although sometimes it is called bipartite and there is some connection between them, but by default, when there is no connection in layer 1 of nodes, and there's no connection between layer 2 of nodes, and there's only connection between nodes of layer 1 and nodes of layer 2, it is bipartite, and there's no direction. It is undirected. We have tree. So tree is acyclic undirected graph. So as we can see, there is no cycle. So we cannot get back to the same node throughout the graph, which is a tree. And we have polytree, which is directed acyclic graph. So this is something you see in decision trees, right? So decision tree is technically a polytree by definition. So as you can see, we can categorize all kind of graphs. So these are 3 of them, mainly by knowing if they're directed or undirected, or if they are cyclic or acyclic. And it helps you to understand how you can formulate your problem, and also better understand what's going on in different kind of articles that you read in graph neural network modeling setting. Any questions so far? By the way, I'm gonna pause throughout the workshop and ask if you have any question. Please, as Dave said, don't hesitate to ask your question. This is a workshop. It's not a talk or just a scientific presentation in very high level. I want to make sure that you understand terminologies, you understand the details, and preferably you'll be able to start using graph neural network for the problem that you're working on. Any question? Okay, so, but the question is, what kind of problem we can solve with graph neural networks? We have different kind of question, and for each one of those questions, the graph generation could be different, and how we can use graph neural network for that problem could be different. We have node selection. So imagine object detection in images. So that is technically a node selection if you consider each pixel to be a node. I just provided a simple example. Sometimes we will want to go through, for example, proteins, or we want to go through genes or DNA or even medical data, and we want to identify a specific data points if we consider each data point to be a node, or a specific part of data points if you want to consider different parts of data points as different nodes. So it will be sort of object detection or node identification in general. So that's about node selection. We have node classification. So that node classification could be about, okay, where proteins are interacting with each other, where there's a, for example, drug-target interaction or so. We have link prediction, for example, if drugs are interacting with targets or not, and we have graph classification. So, and it's about classifying proteins, identifying if proteins that interact with a specific ligand has a specific category, belong to a specific category. right? So we can solve different kind of problem. And as you can see, it depends on how we define those graphs and formulate our problem. Okay, so.
And Ali, sorry to interrupt. We had one question here.
Oh.
Kalyani is asking, I think it's our tree type of graph applied example to family trees.
So family trees could be somehow formulated in polytree, but that also depends on if we have all the information or not, because the sparsity of the information matters in family tree generation.
And Vasudev is asking, can you explain again the difference between node classification and selection, please?
Oh, for sure. So in node classification, so let me go through images because people are more familiar with images, but in throughout PyTorch collabs that we're going to go through, we're going to see the differences for graph neural network. So imagine we have each pixel as a node. Okay, so I want to do object detection. I want to use graph neural network for object detection, and I want to use each node for one pixel, right? So in this way, if you want to identify objects, for example, cups in images, right? So it is a matter of node selection. So which nodes belong to cup category? Okay. But you can reformulate the problem to say that, okay, we have two categories of pixels. Some pixels belong to cups, some pixels don't belong to cup. So it is not a cup pixel, right? So in that case, so you have a classification. Sometimes you may have same problem and you formulate it in different way. Sometimes you may have different kind of problem and you need to go for node classification or node selection. The other example is radiological images. So imagine for radiological images, you want to use graph neural network. So you can go for this problem of identifying boundaries of tumors, for example, or you want to just say that, okay, I want to classify nodes throughout the image as being a tumor pixel or non-tumor pixel. Was that clear?
Thanks, Ali. And then Danesh is asking, how about EMR data? Vasudev said, yes, that was clear.
So yeah, for EMR data, so for application specific kind of problem, so it is a domain by itself. It's like, okay, how about genetic data? So it depends on what kind of problem you want to solve, right? So depending on the problem, if you have a specific problem, reach out to me on LinkedIn, we can talk about it. But if you have a specific problem, it's just a matter of how you want to formulate it and what kind of modeling strategy, what is the best category of methodology if you want to use it for your problem. So graph neural network is a hype, I can say right now. It is an amazing methodology in general as an umbrella of series of models and methodologies, but it doesn't mean that it's going to work for every single problem. So, but if you have a specific problem in mind, please reach out to me. I will be happy to talk about it.
Cool. Okay, and then a couple more questions here. I'll get to these and then I'll backlog some of the questions and we can take them towards the end or the next break. Stefan asks, not specifically a task, but are the graph autoencoders to get something like a graph latent space?
Yeah, that's a great question. That's a great question. Yeah, that's definitely possible. So embedding identification in general, so representation identification is one category of graph neural network modeling. You can do it in supervised manner, which will be like, okay, we develop a supervised learning model and then we use the embeddings at the end, or similar to fully connected or multi-layer perceptron style autoencoder, you can do it in unsupervised manner. Just say that, okay, we have graphs and try to identify embeddings of the features for each node or embeddings of parts of graphs or even embeddings of the graphs themselves. So that is very important. So in graph classification example in PyTorch, we're going to see how it works. Any other question?
Yeah. Would GNNs perform better than UNets in segmentation programs?
So that again, so it is a common question. So that depends on your data set. That depends on the exact scenario that you want to use GNN or any other methodology on. So there is no problem that we can say that this is the category of methodology that works the best for that domain. So it's like image classification. So we have many different models and many different methodologies even used for image classification in radiomic setting, in classification of dogs and cats, in differentiating between different breeds of dogs or different kind of animals. So it depends really on the application. So we cannot necessarily claim that for one specific domain, GNN works better than the other. So because specifically in academia, you are working on a specific data set, most probably. I've dealt with that issue as well. And for that specific data set, maybe a state of the art is not performing as well as you expect. It's not a problem because your data set could be small or in a specific part of feature space. So, but it is very hard to say if in general, one methodology is better than the other for a specific domain. Sorry if I'm disappointing you.
So there's some good questions here. I guess what we could do is maybe we'll continue with the presentation.
Sure.
Please, I don't want to discourage everybody for asking these questions. We will get to them. So we'll just put a bookmark on those, and then when we get to the next break, I'll make sure to ask those.
Perfect.
Okay, yeah, and in the chat here, some people are offering some cool suggestions as well. So thank you for that, Nabila, and thank you, Daniel, as well. Okay, cool. I'll let you continue, Ali.
Thank you. Perfect. So one part of neural network modeling is feature and data transformation. So imagine we want to transforming graphs to a data structure ready to be used in neural networks. So what kind of information we have? First of all, we have graph information, which is our adjacency matrix. We talked about it. It is about connection between the nodes. That matters a ton. The other thing that matters is we have features for nodes. So we want to combine all these kind of information to be able to answer the questions that we have in node level, in graph level. Node classification or node selection doesn't matter, but we want to combine all these kind of features. So, but we have something else as a cherry on the cake. I'm just talking about it here. It is not very common, although it is possible to work on it in PyTorch as well. Some of the convolutional layer graph neural network layers available in PyTorch handle it. And it's about edge type. So we talked about having directed or undirected edge type or weighted or unweighted, but these are four general kind of category of edges we can have. So no difference between the edges, no direction, no weight. We can only have weight for the edges. We can have direction for the edges, or we can even have features for the edges, which is way more complicated, but way cooler if you want to talk about it from a machine learning point of view. It means that imagine social network. People are connected because of many, many reasons. So they are connected in Facebook, LinkedIn, Instagram, and then they see each other, all those kind of things. So they are not necessarily connected because of one reason. So then these features could help us to realize the characteristics of the edges, connections between the people, and also learn from it for any sort of question answering in graph neural network set. But we are not going to get into it to make it more complicated. Graph neural network needs a course, maybe a full semester course. But I just wanted to touch on it to explain that this is also possible to work on. So why do we need graph neural networks? Why not just use fully connected neural networks, multi-layer perceptrons, or convolutional neural networks? So let's dig a little bit into theory behind it and then application. And also let's review what's going on in artificial neural network modeling in general. So imagine our fully connected neural network modeling system. So we have a supervised learning setting with fully connected layers, and we have two important processes. Forward propagation shown in blue, and then backward propagation shown in red. So what are those? Maybe you know about it, bear with me. It is an overview. Just we are reviewing what's going on in this setting. So first, in forward propagation, the only responsibility for this forward pass is to come up with a prediction. If it is good or bad, who cares? It is forward pass. Forward pass doesn't care if the prediction is good or bad. It just cares about bringing the input information in the first layer to the output layer and come up with the prediction of the output, right? So there is a linear transformation between two layers, which is about neuron value summation. So we linearly combine values of neurons by some specific weights, and then we apply an activation function, which is the only source of nonlinearity in this case. And then we go through the step, next layer, and then next layer, many layers. We can have many layers here, right? So this is forward pass. It is about coming up with prediction. Sorry. And then we have a backward pass. So in backward propagation, network checks if the predictions in forward pass is close enough to the reality or not. And based on the difference between reality, real output, and predictions, it tries to update these weights. So these W's and B's that, again, in forward pass, it wants to use to come up with new prediction. So in forward pass, it comes up with prediction, goes through backward pass, it updates the parameters, and goes through this process again and again and again to improve itself. Great model. It worked for many examples. It has high performance for many applications. Why could we not benefit from it in graph setting? It's not about we cannot use it. We can use it, but it is not effective, and we're going to see why. Let me go through maybe a couple of more slides and then go through your questions. So imagine we have this 4-node graph, blue, purple, or magenta, and then light blue, and then we have orange. So there's a problem here. So we need to come up with a feature matrix to be used in neural network in that fully connected setting. And the problem is we need to include both adjacency matrix related information and node features. So what does it mean? So it means that for every node, we have features equal to the number of nodes throughout the graph plus node features, right? So we have to build this matrix based on this adjacency matrix and graph node feature matrix. And the first problem is all the time, the number of features will be equal or greater than number of data points. That's not a good scenario. Maybe you're familiar with curse of dimensionality. So imagine we have 3-dimensional space and you have 3 nodes. How confident you can be for identifying boundaries between classes. Imagine you want to do 2-class classification or 3-class classification. So you want to have more data in that 3-dimensional space to come up with confident boundaries. But there are some other issues as well. So one of them, we talked about it, is number of parameters is greater or equal to the number of data points. That's definitely an issue. The other issue is what should we do with new nodes? So whenever we have a new node, either we have to change the whole feature matrix and retrain the network, or we had to have it from the beginning. So we are going to see in one example, we use fully connected network fully connected layers for for graph modeling. But the problem is we have to mask the graph. So it means that we already knew about the whole graph, and we just try to come up with prediction for some unknown part of it. By unknown, I mean unknown labels. So before we get into convolutional neural network and text models for the sake of comparison, do we have any more question? Seems that we have quite a lot of questions here in the messages. So I'm gonna go from the last question. So what are the node features in your previous slide in addition besides the adjacency matrix? Okay. So adjacency matrix, we know about it. It is about the connection between the nodes. Node features is about characteristics of the nodes themselves. Imagine none of the nodes are connected to each other. Still, we have some features for each one of the nodes. Imagine in social network, we are in a world that nobody is connected to another person, but we have features for every single person. Height, weight, educated or not, or all those kind of things. So we have features for individual data points or for individual nodes, and then we have some information regarding connectivity of those nodes, so how those nodes are connected to each other. Did I answer your question? Perfect. So there was another. Can we use, first of all, sorry if I missed any question, but please type it again if I missed any question. So the question is, can we use PCA? Could you, so you mean in this setting to reduce the dimension? Yeah, it is possible for sure. So the problem again is if you have a new data point, your feature set changes. So it is a general problem for graph. So if you have a new data point in general setting, imagine you're dealing with genomics, you're dealing with medical records or anything, we have features, and those features are the same for new data points, for previous data points that we trained the model on, doesn't matter. Just their values are different. So imagine we are characterizing people, so weight, height, and education, 3 features. Same for every single person, right? But in this setting for graphs, when we bring a new data point, a new node in this setting, the whole process changes because the features change. So that's an inherent problem in this setting. But yeah, it is possible. If we don't care about that problem, for sure it's possible. So PCA is a dimensionality reduction approach, and it's a linear dimensionality reduction approach. So your friend also asked about autoencoder. So autoencoder will be fancier and more complicated version of PCA. So it is possible to use either of them, but it doesn't actually solve this problem of new data point. In some setting, we care about it. Okay, was there any question that I didn't answer? If there was, please either copy paste it again, or Dave, if you know, please bring it up again.
Yeah, there was one more. I have 1 or 2 here. Emert had asked, and sorry if you've covered this. How easy is it to combine neural network architectures, example CNNs and GCNs, maybe at the FC layers in PyTorch? And they said for saying integration images with PPI data, for example.
That's a good example. So it is not difficult. There are some examples. If you reach out to me on LinkedIn, I can provide exact examples. But we're going to get into the code, and you'll see. So the main difficulty is about the network building, the initialization of the network. So imagine you have a graph neural network, and then you have a convolutional neural network, and then you come up with embeddings from each one of them, and then you want to combine those embeddings with fully connected layers. So we're going to see how it works. So just bear with me. I'm going to explain it there.
Yeah, and I think we're caught up.
Okay, perfect. Awesome. I'm very happy people are asking questions. Okay, so about convolutional neural network and then sequence models, text models. So sometimes the question is, why not using convolutional neural network? So it seems that it is closer compared to fully connected layers and multi-layer perceptron for graph neural network modeling. But the problem is, so they have been successful in their specific applications, but graphs are more complex. So we have some issues that we cannot necessarily resolve with these two kinds of modeling. So images are technically two-dimensional or three-dimensional grids. So even if you have RGB, it's just a matter of having one two-dimensional grid for R or red and one two-dimensional grid for green and then one for blue. And for sequence, you have one-dimensional graph. But in general, graphs are more complicated. Let me provide you one example. So imagine we have these two graphs. You agree they are the same graph, right? But if you want to apply convolutional neural network on top of these graphs, it means that you want to use adjacency matrix. But there's a problem here. So these two graphs, just because we changed order of these node naming. So here I call it 0, 1, 2. Here I call it 0, 1, 2. So we are just changing the order of nodes. But it is the same graph. So we can still have same features. Just the adjacency matrix is different in this case. Exactly because of that order change. But you agree, it means that the convolutional neural network now should be able to handle it. So when we want to use convolutional neural network or fully connected neural networks, we need to take care of some stuff. Okay, so it is not only about not having an effective model, we have to also care about some of these order invariance issues that we need to be careful about. Okay, so learning in graphs. So what's going on when we talk about learning in graphs? So let's look at this small graph and imagine we want to come up with some information, some output for node red. Imagine, for example, it's node classification. So we have node features. So we have feature for the same node. So if we dismiss the edges, if we get rid of the edges, we can still predict something about the nodes based on the features of each one of the nodes, but we are losing information about their connection, right? But we want to also benefit from the neighbors, so they provide information. Okay, so first level neighbors. So here by level, I mean if there is only one edge between those neighbors and this red data point. So we want to benefit from the information that comes from these first level neighbors, and then second level neighbors, and then third level neighbors, and so on. But the question is how? And that's the question we want to tackle with graph neural network modeling. So again, imagine we want to do some sort of classification for node red, node 1. So we have some features, but we want to also benefit from the embeddings and features that comes from the neighbors. So we go one step further and we go to first level neighbors. We have a black box here. That black box could be a neural network. So that black box could be a graph neural network layer to collect somehow to get the information from the neighbors and provide that information for classification of node 1. But we don't want to stop there. The question is, how do we want to go further away? Same process. So for each node, we care about its neighbors. Node 2 has node 1 and 5 as its neighbors. So we have node 2 here. Node 1 and 5 are the neighbors. As node 2, 3, 4, 5, 2, 3, 4, 5 were neighbors of 1. Again, node 3 only has one neighbor. Node 4, 1 and 6. Node 4 has 1 and 6. Node 5 has 1, 2, and 6, right? So there are a couple of things here. One, it doesn't matter if we are doing classification for node 1 in this level. It doesn't matter that we have node 1 at the end to do the classification for. We can still provide that information in this layer-wise process for other nodes. So node 1 is neighbor of node 3, so it should provide information for node 3. Although at the end of the day, we want to provide that information for classification of node 1. So in this process, to make it generalizable and very easy to be used for all the graphs and new graphs, we just care about the neighbors, and then each neighbor cares about its neighbors, and so on, right? So, and these black boxes could be mathematical processes. Neural networks somehow are mathematical processes to collect that information, transform it, and provide it for the next layer. So then each node could be an input for its neighbors. One. Second, increasing number of layers will increase redundancy. So if we go back, maybe you say, okay, it's better to go far away. So go as far away as possible. The problem is, even for very large models, even for very large networks or graphs, we don't need to go far, far away. For MSN network with 30 billion conversation, 180 million nodes, and 1.3 billion undirected edges, the average shortest path between the nodes is 6.6. So we don't need to have 10 layers of neighborhood. Maybe 3, 4 would be enough, because neighbors learn from each other. And then number of input nodes of neural network in each layer of neighborhood could be different from each other. And why do we care about it? Because if we go back here, so we should have an operation that doesn't care about number of inputs. So here it should get 2, here it is getting 1, here it is getting 3, here it is getting 4, and all these boxes could be the same. And then we want to train the model for all these different number of inputs. So it should handle all those scenarios. So let's see just 2 or 3 slides math, and then I'm going to get rid of math if you are not a fan of math. But I just want to make sure you understand what's going on behind these kind of black boxes. Any more question? So MSN it's just a data set of the conversation. So messenger conversation. So you can easily search for MSN network. Actually, if you search MSN network 6.6 shortest path, it will provide you a blog that explains everything. Yeah. So there was one more question, I think. So the input to the black box would include both the features of each node and the corresponding adjacency matrix right now. Okay, so that's a good question. So here, so as you can see, the input is this node 1. So what does it mean? So you agree in this process of layer-wise information flow, we already have the adjacency matrix because we know which one of the nodes is neighbor of the other, right? So we don't need the adjacency matrix information anymore. We just need the node features. So here we get the node feature information of node 1 and somehow add it. It's not addition in mathematical term, just combine it with the node feature of node 3 that it had before, and then come up with the new one. I'm going to get into it. That's a great question. So there was another question. In terms of parameters, how much computationally expensive is GNN in comparison to other networks, I suppose? In terms of parameters, neural networks. Okay, so that depends on the problem. Again, we are going to get into a couple of examples and a couple of scenarios that people try to handle the dataset size issue. So we're going to get into that. So, you know, even for convolutional neural network and LSTM, there was some issues regarding handling large data set. So people in time tried to resolve it, and that is happening for graph neural networks as well. Is number of neighbors a hyperparameter? So number of neighbors is part of the graph itself, right? So that then couldn't be a hyperparameter. So we already defined the graph, right? It is based on the data set as well, so answering to the previous question. But regarding the number of neighbors, so we have a graph and we have a specific neighbors for it based on the original graph that we want to train our graph neural network for. And those neighbors are used for the training process, so we are not changing those neighbors. So it is the adjacency matrix. So instead of using the adjacency matrix information directly, we are using it in this layer-wise process. So I'm going to go through the rest of the presentation for the sake of time, and then we can go back to your questions at the end. Okay, so if you remember, this process, this black box process, shouldn't depend on the number of inputs. So how does it work? So one simple example could be if we just add up the features of the neighbors. So with a specific set of weights, we add them up and add it to the feature of that node itself. So imagine, again, going back here, we have node 4. We want to somehow combine features of node 1 and 6 and a feature of node 4 that it had before. So, and these are different terminologies. So ZV is embedding of node V. Imagine node 4 in that case is V. So it's just the index, if you want to call it. And then we have weights that we have to learn, W, A, B. And then we have embeddings or features for the neighbors, which are these ones. And then embedding of the node V from previous layer. Math, if you don't know that much about math, don't worry about it. But as you can see, this part, you all agree. This is a linear summation. And you agree that this linear summation doesn't care about number of inputs. And that's amazing, because we don't want to care about number of inputs, which is number of neighbors. So, and then we apply a nonlinear operation, which is ReLU, similar to any other neural network modeling. So, but these kind of summation could be more general. Instead of just having a sigma or summation here, we can have more complicated kind of relationship. It could be just an aggregation function for neighbor features, and then those aggregated values will be used together to come up with embedding of node V. So it is just about some sort of aggregation that doesn't depend on number of neighbors, which will be number of inputs to that graph neural network layer. Also, that summation, that aggregation should be combined with embedding of that node in the previous layer. Again, it was just very brief summary in the math side. If somebody is a math expert or math enthusiast, so I wanted to just provide it for you. So just a summary of what's going on here. So we have neural nets, we have layers here, and same model parameters are used for all the nodes. So we want to use those parameters for all these kind of feature summation and embedding identification. Number of parameters is independent of size of the graph. If you remember, the problem with fully connected neural network, or in that PCA setting as well, it was we had features that its size, feature set that is size depend on the number of nodes that we have. In this scenario, that's not the case, because we don't have that adjacency matrix directly in our modeling. So we don't have a feature vector or feature matrix that has adjacency matrix itself. We just have the features of nodes. And in this layer-wise process, we take care of adjacency matrix and neighborhood. So, and then it can be easily generalized to unseen parts of graph or new graph. You agree, this is a general process. If we have new nodes, new graph, we can easily generalize it to that. So before we get into application, so that was first part of the workshop, which was about the introduction part. Then we go through few papers about application of graph neural network in healthcare. And the last part, we go through PyTorch to see how it works. Okay, there was another question, I think. Was there another question? I think somebody asked a question, another person answered it. right? GNN is more generalizable NN as compared to CNNs over LSTM. So again, that's so the question is, do you think, I hope that question is for me. So do you think GNN is a more generalizable neural network in comparison to CNNs or LSTMs? So the question is, for what problem and for what data? So even for proteins, if you model, I'm not sure if you're familiar with different kind of protein classes. So we have different kind of protein classes, kinases, GPCRs. So if you don't know them, imagine class 1 and class 2 proteins. If you build some models on kinases, you don't know how generalizable that could be for other class of proteins. And that's about physics of the problem. That's about chemistry behind the problem. It's not necessarily about the neural network itself. So the generalizability, we cannot answer the problem of generalizability solely by talking about machine learning. We have to care about the problem. So they have to be joined, right? So if you have a specific problem in mind, we can talk about it at the end. But at least I cannot claim in general that one is better or worse than the other. Regarding generalizability, we are just talking about generalizability in this question. Okay, so there was another, no problem. So graph neural network in healthcare. So here I provided few examples, few papers that has been recently published. So it provides you some insight how graph neural network has been used in healthcare setting. And we're going to see different, kind of graph neural network modeling so from graph perspective itself. So although the graph neural network layers are different, but the generation of graphs themselves are also very interesting. So this is an example from protein GCN, protein model quality assessment using graph convolutional networks paper. So it is a manuscript in bioRxiv. And the question is, so definitely it is obvious from the title. So they wanted to come up with model quality assessment strategy using graph neural network. And this is a stepwise process. And I'm going to go through each step because each step matters in graph neural network modeling. So the first step is about producing protein graphs. So you have a protein. Each part, these blue, red, yellow, and green, each one of them is a residue. And residue is collection of atoms, right? So you can consider each residue as a node. You can consider each protein as a node. You can consider each atom as a node, depending on the problem that you have. So in this case, because of the problem they wanted to answer, and they were expert in their own field, so they use atom level nodes in this graph generation. So each one of these nodes is an atom, which are non-hydrogen atoms. Sorry, let me drink some water. And then the question is, how should we combine them? So in the next level, they do some sort of local pooling. So they locally try to combine the atom information to come up with new embeddings that are now in residue level, right? So they have atom level features, and then they combine, for example, in this triangle, which are now shown in blue in this level, they combine embeddings or features of these three nodes here in a way to come up with this residue embedding. Or again, for these four nodes as part of another residue, or these four nodes as part of another residue, and so on, right? So first step, build and graph in atom level. Next step, pulling them together to come up with local embedding in residue level. And then they combine these residue using some global pooling and fully connected layers. So going back to one of the questions that your friend had. So to come up with, yeah, exactly. So great point. Resolution matter for sure. So I hope you're talking about resolution graph, not the resolution of the figure. But then they try to come up with their local and global scoring to be used in model quality assessment. So that resolution that your friend also talked about and I mentioned is about how far we want to go into just making our graph more in detail. So if we go back here, we wanted to come up with atom level graphs because we cared about that resolution, but we could in some cases use higher level information. Another example, so this has been for survival of cancer patient prediction. And here you can see this kind of graph. So it is a bipartite graph. If you remember, I introduced bipartite graph. So they have bipartite graph between genes and patients, and bipartite graph between copy number variation and patients, and then some clinical data transformation, and then they use graph neural network on top of these. So this is another example. We don't want to get into details of every single paper, but this is another example, and as you can see, the network generation in this case is different. So it is a bipartite graph because maybe there is no information or we don't care about the information between the patients or between the genes. So we come up with a bipartite graph between genes and proteins and then try to combine them. It could be for medical record, it could be for copy number variation, epigenetic information, protein level information, metabolomic information, doesn't matter. So then you can use them all together and then come up with the prediction. That could be survival of the patient. Again, another example in drug discovery. So it was about combining the graph level information and sequence level information. Again, going back to your friend's question, you can check this paper. This is one great example of how you can combine different kind of models. So here you have a graph-based models. So you have graph modeling here, graph neural network model here, and then you have BERT modeling, sequence-based modeling here, and then they got combined, and then they try to come up with different predictions like water solubility or geometric property, thermodynamic property of different small molecules or drugs in general that they had in the problem. So please check this paper. It is a great paper. So I'm not promoting these papers as a state of the art or amazing papers in their specific kind of application. I'm just introducing for the sake of learning. They are great papers to learn about how to use graph neural network in different healthcare problems. So the title is Advanced Graph and Sequence Neural Networks for Molecular Property Prediction and Drug Discovery. Okay, any question? So have you published this? It is not my paper, sorry. So be sure, I can share my slides. So maybe you can talk with Dave later about sharing the video or slides. I can share my slides for sure, but in case you will not have access to it very soon, just shoot me a message in LinkedIn. I will be happy to provide you some of the slides or all of it. Yep, fine by me. No problem. Oh, thanks, Dave. Great. So let me drink more water. Thank you. It was great to have you here. Great. Unfortunately, I cannot make it to yours. So graph neural network and drug discovery for COVID-19. Sorry. Okay, now it's working. So this was a manuscript that we prepared around 2 months ago. So the concept was to combine a technology that we have in-house, Matchmaker, and a graph neural network, a GCN model that got built in collaboration with Vector Institute to come up with a drug that would be effective for COVID-19. So just an introduction about our Matchmaker technology. So how it works is we have some feature engineering for small molecules ligands and for proteins, and then we combine those features and use it in a deep learning system. So in a deep learning model, and we train it on millions of drug target interactions. So we have a ton of data. So we are lucky, so not lucky actually, the people who founded this company, actually, they knew what they're working on, so they wanted to solve a problem that they had data for. So it means that we can develop a good machine learning model for. So, and then we came up with high accuracy, high generalizability, and high throughput. So that was just an introduction about our matchmaker technology, so that you know what's going on in that figure. Let's go through the graph neural network part of it. So we have a multi-scale interactome. Why do we care about that multi-scale interactome? So when COVID, unfortunately, actually COVID virus goes to different tissues or maybe lung of a patient, it is about interaction between proteins, between different entities. So proteins, so we have these entities here. So human proteins and SARS-CoV-2 proteins, and then we have involvement of human proteins in different functional pathways, and then drug compounds affect different proteins for sure. So it's just about how to combine all these information. So that's the tricky part. So we wanted to benefit from all these information because it is not a simple one hit kind of scenario to say that one drug goes and hit a specific protein and boom, done. So that protein will interact with a ton of other proteins in different functional pathways, and there will be an interaction definitely between the SARS-CoV-2 proteins and human proteins. So, and then there was a embedding building for each drug using convolutional neural network. So you can read the details of the paper. It is again just a summary of what was going on in the paper. So we had embedding building using graph convolutional neural network, and going back to your friend's question, we had embedding optimization using unsupervised learning in an unsupervised setting. And then GCN model determined the potential efficacy of drugs or protein targets, right? So that was the process. Again, it was a short summary of what's going on in this manuscript. So please go through it and read about it. If you have any question, I will be happy to answer them. But let's get into a more exciting part if you're a hands-on person in machine learning setting, and we want to talk about graph neural network modeling using PyTorch. Any other question? Okay, so graph neural network modeling using PyTorch. First of all, so from now on, it will be heavy coding and heavy software development discussion. But by heavy, I don't mean I'm not going to describe it. I'm going to describe every single detail, but I'm going to go through the code line by line and describing how it works in PyTorch. So this is a very simple example from the introduction of graph neural network modeling in PyTorch. PyTorch geometric. So torch geometric in PyTorch is amazing. Ton of content there. You can learn about graph neural network modeling in general, theoretical aspect of it, how to use PyTorch for it. And actually, we are going to go through some collabs provided in Torch geometric for the sake of actually clarity. Also, you will all have access to it. So when we talk about, oh, one more thing. In Torch geometric, there is a data sets part. So on that data set has a ton of different data sets. One of them is Planzoid that we are using in this exam, right? So for any sort of neural network modeling in PyTorch, there are 3 steps. It is the same in TensorFlow, just the syntaxes are different, some aspects of it are different, but this is the general scenario. 1, we want to initialize the network. This is the initialization of the network. It means that we have 2 convolutional, so this is only the name, so don't care about these names. I can call it eggplant 1, eggplant 2, who cares? But because we are writing a graph convolutional neural network code, we don't want to call it eggplant, so we will call them convolutional 1, convolutional 2 for the sake of clarity. If you want to use number of layers or kind of layers as hyperparameter, I suggest you go beyond it and don't necessarily build these layers one by one and go for a loop and try to make a list of layers, but it will be more complicated just if you are expert in neural network, not expert, have experience in neural network modeling, this is how I suggest you have layers as hyperparameters of the model. So then we have GCN_conv from torch underline geometric.nn. So torch underline geometric.nn has all the layer types you need for graph neural network modeling. Okay, so you import GCN_conv, and then you have a specific number of input node features that depend on the problem you have. Maybe for some problems you have 50 features for each node. For some other problems, maybe you only have 6. This here, and then number of classes, because it is a classification setting. The next part is the forward propagation. So it is exactly similar to the theory. So we have an initialized network to just say that, okay, these are the layers and these are the size of the layers, and then we have forward propagation part, and then we'll go through the backward propagation part. So in this forward propagation part, as you can see, we are adding a couple of things here. So we add ReLU. So in this conv1, we just get the input features and then do those kind of graph neural network kind of operation, which was the aggregation and so. But if you remember, we had a nonlinear function to be applied on top of it. So here we are using ReLU, and then we have dropout. Let me explain what's going on here. So ReLU is a simple nonlinear activation function. It is very common in neural network modeling. If you don't know about the details, you can easily read about it. It is the simplest possible. So it is just a matter of if x is positive, use x. If it's negative, set it to 0. That's it. But it is nonlinear, you agree. So, and dropout is a genius kind of regularization system. And this is how it works. So maybe you're familiar in general about generalizability and regularization. So in traditional regularization, maybe in a sparse learning, in ElasticNet or Lasso, maybe you know that sometimes we regularize weights to make sure we will not have huge weights and try to avoid any sort of overfitting. So in this case, in dropout, we are assigning probability to contribution of neurons, to each neuron in their contribution in the layer-wise process of neural network. So it doesn't mean that that neuron definitely will be removed. I mean, its contribution, but it means that they have higher than 0 chance of being removed. So that's important. So it means that some of those neurons will be removed. So again, it is between convolutional layer 1 and 2, and then we have this log softmax just for the sake of classification, because the information we get from these will not be class 1, 2, 3. It will be an array of continuous values, so we have to transform it to use for classification. That was forward propagation. If you've done any other kind of neural network, it is the same process, just we have different layer here, which is GCN_conv. Then we have backward propagation. So backward propagation, again, is not very complicated. So honestly, the coding part is not complicated at all. And they are great Colab notebooks that we are going to go through, and it will help you a ton to start working with graph neural network modeling in PyTorch. So we need to work. So there are a couple of stuff here about GPU versus CPU. So let's not get into that detail. But there are 2 important steps here. One, initializing our optimizer. Because if you remember, in forward propagation, neural network comes up with prediction. It is not optimizing anything. It just predicts. So optimizer is important for backward propagation because it tries to optimize and adapt weights and parameters of the neural network to make the predictions better in the next round of forward propagation. So, and here what we do is we calculate loss. So NLL is just negative likelihood loss. And then we apply backward So we calculate loss, we calculate gradients and so, and then optimizer.step just do parameter update. That's it. So we calculate loss, it calculates the gradient, and then it goes through parameter update. And this process is repeated for each epoch. Very simple. So these are three very, very important links. Just by these three, going through all of it, you will learn a ton about graph neural network modeling and graph neural network modeling in PyTorch. So there's an introduction page in PyTorch. So PyTorch-geometric, you'll find an introduction page here. Torch_geometric.nn has all the necessary information you need to know about different layers for graph neural network modeling. And you have access to many great data sets for graph neural network modeling. These are graph data sets. These are designed for graph neural network modeling. Any question before we get into Colab notebooks? Okay. There is one question. GCN building block. So you mean math behind it, or so could you clarify your question? I'm not sure if I get your question. So the question is, can you briefly explain the GCN building block? So the high level intuition is it tries to aggregate information from the neighbors, but it tries to somehow normalize it based on degree of neighbors. So if we have a high degree neighbor, it normalizes it to that high degree neighbor. So to make sure the contribution of one node with ton of edges will not dominate the rest of the nodes. I hope it answered your question. Okay, perfect, awesome. Okay, so let me explain these, and then we go through the Colab notebooks themselves. So these are different notebooks available in PyTorch Geometric. So there's an introduction one with a ton of information regarding visualization and how in general graph neural network can be done. In PyTorch Geometric, there's a node classification with graph neural networks, and there's a graph classification. If you remember, you can build graphs and try to classify each one of the nodes, or you can combine information about different nodes to classify the graphs themselves, right? So we have scaling graph neural networks, which we're going to go through, and then point cloud classification. We are not going to cover point cloud classification, but in general, the concept of point cloud is also very interesting. So they've had a ton of application in object detection or object categorization and classification in general. But imagine you have, for example, an airplane, and you want to identify different parts of airplane from images. So point cloud helps you. Even for protein classification, people have used point cloud classification for sure. So explaining GNN model prediction using CapTom. So we're going to go through this example. This is a great example. If you have time, we're going to cover that as well. But these are different tutorial style Colab notebooks you can use to learn more about graph neural network modeling. Even if you don't know about neural network modeling in general, I think these will help you to kick a start in graph neural network modeling from scratch. So I'm going to finish my slide deck and then go through the Colab notebooks. First of all, thank you for your attention. This is my email, so in case I forget to tell it at the end. And you can reach out to us in LinkedIn and in Twitter and check our website for sure. I think some people have dropped to go to the other session. So we're getting into the software development part, and maybe not every single person is interested. So let me stop sharing my slide deck and then go through the code. Sorry for the background noise if you hear any sort of background noise from my laptop. This is a graph classification code. So you can go to PyTorch Geometric Colab, so I provided the link. So let me go through the slide deck again. So this is the link. So PyTorch geometrics. I can pause here if you want to get access to it. So go through this link. I can pause maybe for a minute or two. So this is a graph classification example. So there is great visualization here that clearly shows you how it works. So we have the whole graph. Let me zoom in a bit. So we have graphs for molecules, and then graphs of molecules are used to come up with embedding for each one of the molecule. So then each one of the molecule has one, for example, feature vector. So that will be an embedding of features. So set of embeddings for that data point, and then we repeat it for all the data points, and then try to come up with a boundary to classify molecules, right? So this is a good example because it relates to healthcare. So the graph classification, so this is what is the description in the Colab notebook. The most common task for graph classification is molecular property prediction, in which molecules are represented as graphs. So we covered it, and the task may be to infer whether a molecule inhibits HIV virus replication or not. But you agree. So we have molecules, we can have different kind of classification scenarios here. It depends if we have the data for that problem. So this is a great data set. So if you run it, so I ran it already, so we can run it, so there shouldn't be any sort of issue. So the first part of the code tells you about the data set. So this is the number of graphs. It is a very small data set. You have number of features and number of classes. So it means that each node has two classes. So it is binary classification for nodes, for graphs. And then we have number of features per node, right? So we have 17 nodes, and this is for one example, sorry. So this is for the first graph. So we have 17 nodes for the first graph, 38 edges, and so on. And definitely it is undirected. So it is a very simple example of undirected graph. So I'm not going to get into some of these GPU kind of explanation, but let's get into the code that we already covered in our slide deck, and you can read through the rest of it. Again, I mentioned if you have any question, I will be happy to answer your question even via LinkedIn. So don't hesitate to reach out to me. So this is the neural network, graph neural network modeling part. So we have linear layer at the end. We have convolutional, graph convolutional layer from torch geometric.nn. We have global mean pool. So why do we need global mean pool? Because we want to aggregate the information and provide the embedding in graph level, right? We don't want to do node level classification, so we need to pool that information. It is somehow similar to that pooling of information from atom nodes to residue embeddings in case of the example I had in the slide deck. But let's get into the code. So we have convolutional layer 1, convolutional layer 2, convolutional layer 3, and then linear layer. So these ones are all the same, similar to fully connected neural network or convolutional neural network. You need to just specify some parameters, in this case, number of input, number of output in that layer. So in the first layer, number of inputs is number of node features, and then hidden channels, then hidden channels, hidden channels, hidden channels, hidden channels. And the linear layer, we have to output a vector with the same size as number of classes. So again, in the first part of forward propagation, we have that convolutional layer plus ReLU. If you remember, we can add dropout here. Usually dropout is a great idea if you have many, many features. So maybe in this case, it doesn't matter much, but you can try. So then we have a readout layer for global mean pool, as I described it. and the final classifier. Now we have a dropout in the final layer, but as I mentioned, you can also add it in these middle layers. But that's a matter of hyperparameter optimization, because having a dropout, not having a dropout, what would be the probability of dropout, and where would be the dropout layer? These are all hyperparameter optimization questions. And then we have a linear layer at the end, and then we output that linear transformation. Okay, so we have a question. Is it possible to connect over LinkedIn or Twitter? For sure. So I think I already mentioned you can follow me on LinkedIn. So Ali Madani. So in LinkedIn, I'm under AM Learning. So follow me on LinkedIn. If you have any question, just reach out to me. If you have, for any reason, just point of conversation around machine learning, neural network modeling, if you have any sort of business question you want to start applying machine learning for, I will be happy to provide some feedback and start a conversation. Okay, so this step is going for training and testing. So we already built our GCN class. So a GCN class, similar to other neural network classes, has an initialization part, definitely, and has the forward part. And we usually put the backward part out of it in the training process when we go for epoch by epoch process of forward and then backward propagation. So the whole process of training and learning. So and as you can see here, we have a train function that just gets the data. So these are just some terminologies in PyTorch. Don't worry about it. This is just a data object. So it iterates in batches over the training data set. So here we come up with the predictions. Again, perform a single forward pass. We identify the loss in that forward pass. If you remember, in the forward pass, it's just a matter of coming up with prediction. We go for backward propagation based on the loss that got calculated in this step. So forward pass, identifying prediction, calculating the loss, and then using that loss to go for gradient calculation. And then we go for parameter update using those gradients. And then we clear the gradient. So that is very important. If you're doing any sort of neural network modeling with PyTorch, if you don't put this, the gradient will be added up together in the process. So just zero sorry, will clear the gradients. And then we have the testing, which is just a matter of coming up with prediction and then coming up with predictions in classification setting, because this output will be just probabilities. So the scores, the continuous scores, and then we come up with predictions by using this argmax. It means that if you have, for example, 3-class classification, so you choose the class with maximum probability, maximum score. So then you will add up number of correct predictions. This is not specific to graph neural network modeling. This is a general setting. Then correct over length of that data set will be accuracy. So it's just a matter of number of true predictions over total number of data points. This is a general definition of accuracy. If you train it for 200 epochs, the test accuracy will be 76%. As you know, in any sort of machine learning modeling, we care about test accuracy. So we have one question. So maybe you've already mentioned it, but in terms of API, is this also available in TensorFlow? There is neural structured learning API, same. So in PyTorch and TensorFlow are somehow in parallel, right? So these are different frameworks. That's a great question. So PyTorch geometric is definitely, it is clear, it is specific to PyTorch, but TensorFlow, if you check all their the portal and search for graph neural network TensorFlow, you'll find also some Colab notebooks, also some tutorials, but I haven't provided the link. So it is just based on PyTorch, because mainly it's just a matter of the time. So we cannot cover all of it. So this is an optional exercise. So if you have access to the code, I want to pause it here for maybe 2-3 minutes. You try to complete these parts. These are missing parts, because if you run it, you'll get this error here, and the error here is just because of these missing lines. So fill out these missing lines, and you don't need to invent anything. Just go back to this and try to benefit from these lines. Just use this new layer. So why do we want to use this new layer? So based on this explanation, and you're going to see the result also based on the results we get, this layer will work better on this problem. So there are some theoretical aspects behind it, but just try it out right now, maybe for 2 or 3 minutes. It is a good practice. It is a very easy practice. I'm going to do it, and then we'll see how easy it could be. And then we go through the next Colab notebook. Any question? So I want to ask a question, but take your time. We have still around 15 minutes till the end of the workshop. And my question is, why did you become interested in graph neural network? Was there a specific problem? Was there just because it is a new kind of, not very new kind of modeling, but it is now a hype? So I want to know why you became interested into this. Okay, so similar to many other programming practices, if I'm going to do it as you would do most probably, but if you are new, the only thing you need to do is to just copy paste here, come here, and then see how it worked there. This was based on the other graph neural network. Okay, so if you want to do this, you have to go back to the tutorial, make sure the parameters are the same, the input parameters are the same, but we already checked it, and this is a simple example, so I already checked it. So it is the same, so we can easily just change this network, this. It should work. Let's try it out. So go for our application domain. Cool. So you care about your application domain. Maybe you don't want to share your application domain, but I would be happy to hear about it more. So trying to build a conversational, oh, wound care. Wow, nice, nice. So for wound care, are you trying to model skin? So how does it work? Because I don't know exactly how it works. So trying to build a conversational agent, wondering if this will be useful in this use case. That's another good point. I may be able to find some examples for you. So, it's just a matter of healing prediction. Okay. So I'm very much interested to know how you want to use graph neural network, if it's will be a matter of modeling skin, or it's just high-level features about the wound and about the strategy, the treatment strategy. That's awesome. That's awesome. Great to hear. So, and as you can see, simply by changing that initial layer that we have with GraphCom, it worked. But the practice is not to copy paste and directly use it and directly change the layer. Go to the help of that layer, or find some examples with exactly this layer and try to use it in that way. So because I already checked it, so, and I already used it before, so I did it in this way for the sake of time. But the practice is not to always copy paste one layer and then use the same set of parameters for the new layer. Also, this is usual, and it works usually for many Python libraries, because people try to make it general for different scenarios, like in PyTorch, scikit-learn, TensorFlow. Okay, another example. I'm going to close this one. So another example is node classification. I'm going to send you this. So I'm going to go through it very fast because we have only 9 minutes. So for node classification, again, some description of the data. The question is classifying nodes. So this is not a healthcare data, so I'm not going to spend that much time on it. But as you can see here, this is the way we can implement multi-layer perceptron. So I just wanted to present it to answer one of your friend's question, which was about how could we use multi-layer perceptron at all? Or what's going to happen if you use multi-layer perceptron? So it is possible, it is not effective. So this is the way you can use multi-layer perceptron. You have linear layers, but we have to use all the graph and just mask some part of it for the test set. As you can see here, the accuracy is 0.59. But if we use graph neural network, GCN conv here instead, so we are changing the layers. It is almost that simple in these simple examples. So we come up with test accuracy of 0.81. So more than 20% boost in performance. Okay. So the last example I'm going to go through. So this is a scaling concept. So let's forget about data set. You can go through it. So there was a paper in 2019 called Cluster GCN. So that paper focused on this problem that sometimes our graph is huge. So and we have some sparsity in the graph. And it is not necessarily sparsity. It's just a matter of we have some highly dense neighborhoods that are maybe connected in a very loose manner with just one or two links to each other. So the question is, how could we benefit from those dense neighborhoods and design an algorithm that doesn't have to deal with large graphs altogether? So this was the idea behind a cluster GCN. It was about building clusters and training graph neural network on those clusters independently, but to make sure we are not losing that much information between the clusters, they also consider some between cluster links. So this is the process. So they, in each epoch, so for example, epoch 1, they come up with cluster and develop a cluster-based neural network. So they don't have one neural network for each cluster. So it's one neural network for all the clusters. And then they try to come up with some sort of links between the clusters. Okay, so if you go, something I wanted to show you, if you go to the graph neural network part of it, so the network initialization part of it and forward, it is the same. So it is very similar. So this is what you need to know for neural network modeling in PyTorch. But when you want to develop a machine learning pipeline, deep learning pipeline, neural network pipeline, a better term. So the concept is to use this neural network class and then try to apply backpropagation on top of it, then maybe add some data processing before applying neural network. So the complexity doesn't necessarily come in coding this GCN class. So the complexity is usually for building the whole pipeline or in the process of hyperparameter optimization and coming up with the best model possible. So that was about this workshop. We covered many things, some of them very shallow because this was a workshop. I just wanted to kickstart this concept of graph neural network and its modeling in PyTorch for you to make sure you will be able to start working on it, read more about it. But as I mentioned, if you have any question, if you want to know more about it, first suggestion, definitely go through PyTorch tutorials and all the notes, blogs related to the PyTorch website, PyTorch Geometric itself, and reach out to me if you want to have any sort of conversation, if you have some difficulty applying neural network or graph neural network on your problem. And in general, if you want to have some sort of conversation, for example, the healing prediction example that your friend mentioned, I would be happy to know how exactly it is working. So it is very exciting. People are using these kind of modeling for different problems. And as machine learning enthusiasts or expert, we are all interested to know about different applications, because it is not only about, okay, this model works in this way for this application. It provides insight, how you can use it in future for your own application. So let me stop sharing and giving back the stage to Dave if he's here. Okay.
Hello, hello. Yeah. Oh, there we are. Oh, and I have the galaxy background. That's interesting. Thank
That's
you
a
so
nice.
much. Yeah.
Nope.
Ali, thank you so much. You've been very generous with your time. I really, really appreciate it. I really enjoy how you're answering the questions for everybody and making yourself available afterwards. It's really generous, and thank you so much. I
No
think
problem.
you've helped a lot of people today, and hopefully we'll continue to through the communications afterwards. So I hope everybody enjoyed this. I hope you found it helpful. As Ali and as somebody had asked, we will do a little bit of work to edit the videos. We usually do that. It usually takes maybe a week or two after the conference wraps up, and then we'll provide a high quality video with some of the questions and such that were asked, so that we can send it over as a package for everybody afterwards. And I hope that helps absorb all the density of the information. But thank you so much, Ali. Really appreciate it. I hope we have you back again soon. And yeah, Shriyansh,
No problem. For sure.
Shriyansh, this will definitely help me get started with GNNs. Yeah, no, that's great, Shriyansh.
Good to
Glad
hear.
to hear. Yeah, and anyway, so we have one more session, I think, for the rest of today, another workshop, and then we'll see you on the platform tomorrow. Check the email for Hopin, a notification, and we'll see you tomorrow. Thank you so much, Ali. Really appreciate it.
Thanks, Dave. Have a good day.
You
Have a good
too.
day, everyone.